crystals. Okay, I mentioned another thing about ceramics is that most of the ceramics we will deal with are not chemically reactive. They're very resistant to chemical attack, and that's important. That makes them durable for use as prosthetic materials. And however, many ceramics are actually chemically reactive. Take, for example, sodium chloride, table salt, which many people don't think of when you mention the word ceramic to them. But it is a rock, it's a ceramic, it's a reaction between sodium, a metal, and chlorine, a nonmetal. And it is quite soluble in many fluids, including just simple water. However, the difference is that most of the materials that we will deal with are oxides. And they're a combination of one of these wide variety of metals with oxygen, because oxygen is so prevalent in our environment. And the metallic acting element, which is also very prevalent in the Earth environment, is silicon. And so silicates, combinations of silicon and oxygen to make ceramics, and sometimes with other metals added to them also. Silicates are the most common types of ceramics that we will encounter. And that's important because silicate ceramics and non-silicate ceramics form different structures with different properties. So a non-silicate ceramic would be a ceramic that has, for example, a composition of magnesium oxide, where magnesium is not silicon, and that's why we call it a non-silicate ceramic. The example here actually fits the situation of magnesium. If these four ions are oxygen anions, and this is a magnesium ion in the middle, and if there's an oxygen behind the board, behind the magnesium, and one in front of it that are not shown, then that would be the structure of magnesium oxide. And we learned before about metals that they tend to form close pack structures. Well, non-silicate ceramics form almost close pack structures. You'll notice that this example on the right of a ceramic material looks a lot like an interstitial solid solution from metals. And so this is a rare case for ceramic where the cation would be exactly the right size to fit in between the anions. The case on the left is more typical, where the cation is just a little bit too large to fit, and it squeezes in anyway, and it forces those anions to be slightly separated from each other. So the non-silicate structures are mostly close packed. In contrast, though, the silicate structures are not close packed at all, and this will affect their properties. This will be important. But to give you an orientation, these white looking balls down here are oxygen anions, and the small black balls are silicon +4 cations, and each silicon cation will be surrounded by 4 oxygen anions. Only 3 are shown in this picture because the 4th one is either on top of the silicon or underneath the silicon, alternating back and forth. And so each of these silicons will be in the middle of a triangular pyramid there, with another one on top on the point. There's another oxygen. And those pyramids link up with each other, connected by the oxygens, what we call bridging oxygens. and they form these rings. And the ring has a bunch of empty space in the middle, what we call free volume. And so there's a very low packing factor. And so this leads to silicate ceramics having a much lower density compared to non-silicate ceramics. They have a lower, CTE is coefficient of thermal expansion, which is how much they get bigger when they're heated and how much they shrink down when they're cooled off again. So a material with a low coefficient of thermal expansion will stay almost the same size whether it's heated or cooled. And a material with a high coefficient of thermal expansion will get a lot bigger when it's heated in a furnace. And when it's cooled back down to room temperature or body temperature, it'll get a lot smaller again. And so silicates have a lower coefficient of thermal expansion because as they're heated and they vibrate, they have all of this empty space in the middle here to vibrate into, so they don't have to push apart from each other as much. Because they have some empty space in them, they're more susceptible to crushing, so they have lower hardness than non-silicate ceramics. And because they are less closely linked, they are less refractory. They have lower melting points. If I can get the slide to advance there. Another important aspect is that silicate ceramics are difficult to crystallize upon cooling. They tend to form glasses or amorphous solids instead of forming crystalline solids, and this will affect their properties. And so if we have a non-silicate ceramic and we cool it, we melt it and we cool it rapidly, it will behave fairly similarly to a metal. It will tend to automatically form lots of microscopic crystals in the structure upon cooling, and we would expect it to be fully crystalline after it solidifies. However, if we have silicon in a ceramic, then it has a very complex structure, and in a complex structure it's more difficult for the atoms or ions to all get into their proper places upon cooling to form a crystal. And so the more complex the material structure is, the longer the distance before the structure repeats again, the more likely it is to not crystallize upon cooling, or to require a very, very slow cooling process in order to crystallize. And so the silicate ceramics can be crystallized, but they will tend to be amorphous and not crystalline. That's a material that we also refer to as a glass. The difference is that if you look at the structure here, the glass has a short range order, and the crystalline structure also has a short range order. The crystalline structure has a long range order, but there is no long range order in the glass or amorphous material. So what's the difference between short and long range order? Short range order is your immediate nearest neighbors. How many of them are there? What is the angle of the atomic bonds between them? And so if you look in the silicate crystal, we have each silicon has 3 oxygens it's bonded to within the same plane, and 1 out of the plane that's not shown. Each silicon in the amorphous structure, the glass, also has 3 immediate nearest neighbors, their oxygens. In the ceramic silicate, I'm sorry, in the silicate crystal, there's each oxygen ion has two silicon ions that it's connected to. This oxygen has two silicon ions it's connected to also. And the same thing can be said of the amorphous structure. Each oxygen bridges two silicons with each other. So they have the same short range order. However, looking at the long range order, we can see a lot of long range order in the crystalline case, but the number of second nearest neighbors and third nearest neighbors and the number of tetrahedra in the ring can vary in the amorphous structure. And this leads to it having more free volume. You see more empty space in some of these rings because of the lack of long-range order, which gives it lower hardness and lower coefficient of thermal expansion than crystalline silicates and non-silicate ceramics. So glasses are a type of ceramic that have the lowest hardness and the lowest density and the lowest coefficient of thermal expansion of all ceramics. Glasses have lower properties in these areas than crystalline silicates and lower properties in these areas than non-silicate ceramics. So that's an important ranking. And let me go back for a second. Some people have difficulty with the concept of short and long range order, so I'd like to give you another way to think about it, something from common experience. You can imagine the case of long range order for the crystal of being like apartments and apartment complex. Each apartment has another apartment like it to the left and to the right and across the hall. But if we go to houses in a housing subdivision, each house will have a house to the left and to the right, and one maybe across the street, maybe at an angle to it across the street. The angle between the nearest neighbors will be variable in the case of the housing subdivision. And the size of the blocks will be variable too, but in the apartment complex, in many apartment complexes, it's exactly the same in all directions. And just to let you know, and to tie this back into the relevance to dental materials, these different types of ceramics, the glassy amorphous ceramics, the crystalline silicates, the crystalline non-silicates, can all be combined, and typically are all combined, to make each dental ceramic. An example would be dental porcelain, where you see here under the microscope this material has been polished and then etched with acid to reveal the size and shape of the microscopic crystals. We see that we have some large silicate crystals known as lucite in the structure, and then we have smaller crystals. I forget for this particular microscope photo if the smaller crystals happen to be another size of lucite crystal or if they are aluminum oxide crystals like we'd see in aluminous porcelain. And then you see this darker phase that's filling in all in between the large and the small crystals, and this is a glassy phase. So we have, if this is aluminum oxide, small crystals, and lucite, which has a big formula I won't write for you, and the large crystals, and then we have glass in between them. We actually have all three classes of ceramic materials that we've talked about so far mixed together to make one dental porcelain.